open the same page. Okay, so can you hear me? Can you see my screen?
Yeah.
Okay, so yeah, we stopped yesterday. So we stopped yesterday on the discussion of the, as we say, consequence or test of general relativity, and one was important. This is the angle. Wrote here. This is the shift of Mercury perihelion, which is 33 seconds, and I just write this formula. I don't remember. I send you just to see our book Foundation of Celestial Mechanics. No?
Maybe not.
Maybe not. So maybe, you know, I can't share this book because this book was published in Springer, and the publishing house all time, you know, check. I know, I mean, not happy when you know there's a book which is sell distributed, but in principle you can find it in internet. So this is. I will say why. Manico and Capaccioli. Foundation of Celestial Mechanics. This is a very fresh book. It's appeared just in the beginning of this year, and you can find there detailed proof of this formula which I wrote here. Now I want to find it. Which page? Okay, it's called Two-Body Problem in General Relativity. 204. Just want also to look some things. So there you can find all proof, and what is beautiful that in principle and why. So this is book about big book and about classical mechanics, but why we could represent the proof of this relativistic effect, because it's not important to know deeply general relativity. Only no, it's of course it's important, but we can avoid it as soon as we know the Schwarzschild metric which we wrote before. So after this, we just can use the Lagrangian representation and to obtain this this formula for the shift of the planet perihelion. So it was very important because this strange angles, strange deviation from the classical mechanics was finally proved in general relativity. And this is one of the great tests of general relativity. So, of course, it was checked also for another planets. And you can check, for example, which value of this delta theta will be for Earth or for other planets. So it's understandable that it will be even less. Also, what is interesting that, of course, this idea to check general relativity all time. So it's all time for with us. And just I'll just exactly look on this reference in our book because there is a paper in Astronomy and Astrophysics published. I will write the first author, and maybe you can find it on the internet. In the end, I will, for our lecture, I will try to finalize everything and to show you a beautiful presentation. But now we are writing. So the journal Astronomy and Astrophysics 2020. So you can find it on the internet. And the title of this paper is like this: Detection of the Schwarzschild precession in the orbit of the star S2 near the galactic center, massive black hole. So the idea was the following. We know that in the center of our galaxy, in another galaxy, we have a supermassive black hole. And now the technology is such a way that we can follow for the stars which are orbiting around black hole. So this supermassive black hole is really far from us. It's the center of our galaxy. We are on 8.5 kiloparsec, 8 or 9, around 9,000 parsecs. It's really very far. But we can see what's happened in vicinity of black hole in our galaxy. And there are different stars with different orbits. I just schematically draw like this. And one of the star, I'll draw it not so beautiful. Okay, I leave like this. One of the star, which have a name like this, S2, just by enumeration at the beginning, it's moved such a way that the perihelion is really near to black hole, so supermassive black hole. And a few years ago, it was used as a very technological things, the technological spectrometer on a very large telescope in Chile. Is this project called Gravity, where they gravity. The project, and it was idea to check is it really correspond this the motion of the star is correspond to the case which was predicted by general relativity. So it's understandable that it will be also the shift of perihelion of the star. Since the star was exactly, I don't remember exactly, but like 2018, 2016. Later I will show you a presentation, and who was present my lecture, my course of lectures, Gravity from Aristotle to Black Hole, can remind this. Exactly this year, the star go pass through the pericenter, and it was an effort that it was measured very. And what is also important, the star already investigated during 20 years, so a period of the star is approximately 15 years. And it's understandable that we can, for this case, to look at how this perihelion is shifted. So it was proved that even for the star S2, not even, but it should be like this. So the general relativity is satisfied. For not 15, 16, but it's not so important for this case. It's right here. Period, approximately 16 years, period of S2. You can calculate using this formula, which I wrote here. You can calculate if we know this orbital elements of this the orbit of the star. So I also taken into account the black hole in supermassive black hole. Okay, now galaxy, this is approximately 4 multiply on 6 solar masses. The angle for the star, it's approximately 12 minutes. So of course it looks like, oh look, it's a great, it's a larger than for the case of Mercury, but we understand that the center of the galaxy, so this is supermassive black hole, so this is all of this is center of Milky Way. So but it's really far from us, and it's incredible technical discovery which was made, and now, and by the way, these investigators also obtained the Nobel Prize for Gensel and Guess for the investigation of the motion of the star, not only as two, but stars in vicinity of supermassive black hole in center of our galaxy. As I already said, maybe before, it was in the title of the Nobel Prize, which was given like 2 or 3 years ago. It was wrote that not clearly said that for discovery black hole, but it was said for the investigation, don't remember completely, but investigation of the compact supermassive object in center of our galaxy. So as you can see, it's, you know, in any case, up to now, sometimes even Nobel Committee try to avoid to say directly that it was discovery of supermassive black hole, but we understand that it should be supermassive black hole. So, okay, this is just a few words which I would like to say about this. There is also the test. This is the first, for example, the second. There are many tests of general relativity. About some of them we already discussed. So some of them we already discussed. I mean, the deceleration of time, and as a consequence, this is redshift. I just also want to say about how it's better to say in English. Just a second. Deviation of the angle, deviation of the light which pass the vicinity of the massive body. So in principle, when we speak about classical mechanics, we also have such a kind of effect. But in general relativity, so it means that if we have some mass, and we have some I schematically will draw like this, some light, some electromagnetic wave. So it will be some electromagnetic front. So it will go like this. So it will we will have a deflection of this ray which pass the massive body. So it's a massive body with a mass m. So this is observer, and as a result, observer will see the shifted images. So if before it was star here, galaxy, so we will see it here. And this angle, let's call it alpha, for example, alpha equal to gravitational radius. Don't remember, I use big arrow, small, okay, small, divide on r. So for classical mechanics, how many? It looks like we have some storm. In classical mechanics, it's gravitational radius divided on 2. So the difference only on the 2, on the multiplier 2. The point that and of course it's also as in any prediction discovery was some interesting story, because when Einstein in the first calculated this angle, which it should be in general relativity, he exactly made a mistake. And to discover this effect of deflection of the light, the idea was to look on the star, but how you can take into account this, especially if we speak about the beginning of the century, of the previous century. So it was 1916, so Einstein obtained this expression. The idea was such a way that, okay, let's consider the star when nothing between the star and observer. And the next time, if something, nearby the star, between observer and the star. So this is observer, okay? What means something? And which exactly body can product enough gravitational field in our solar system to deflect the light from the star. This is sun, of course, but it's so understandable that sun is so bright that we can't see any star or like any object in the vicinity of the sun. And it was an idea to consider the obscuration, eclipse, too, of course, eclipse, the solar eclipse. And it was the idea exactly to make, and in this case, you can compare the position of the object, the vicinity of the sun, when it's eclipse, when there is an eclipse, and when anything on the side of light between observer and the object. So this was made, and the first test planned to do immediately, but it was the First World War, and finally the expedition didn't succeed with this because it was sketched by German military and like this. So later in, if I correctly remember, 1918, it was made this observation, and it was proved that really the deflection correspond what exactly was predicted in general relativity. So now, little bit later, not a little bit, it's enough later, in 1930s, it was one of the equation of one of the colleague of Einstein. But but if we will consider for example, the situation when the star exactly on the one, observer and star on one line, what we will see, and it's interesting to look at which effects we will see in this case. And Einstein wrote really very short notes in a journal. It's just one column, where he showed that in this case, the observer will see, instead of to see the star, he will see the circle. So the thickness of this circle, this one, correspond to the to the thickness of the object of the star. So, and this we call Einstein ring. We found the radius of this ring, everything. But the idea was such a way that he said that, look, it's important. It's this effect, for example, between us and star. There is some mass, star in our galaxy. There is some mass, and the mass, hidden mass, and star in one line. Instead of star, we will see the ring. It's like now it's called gravitational lensing. When you are, for example, using some lens, and when you look on some object through this lens, you can sometimes see some strange images depend on the curvature of the lens. The same property has a gravitational, this effect of gravitational deflection of the light. But Einstein says that it's impossible to observe this this effect because the Einstein radius, this one, it will be so small, so small, so that any instrument can't discover or observe this. So, and this idea was, and this note was forgotten for some times. Later, and okay, I would like to finalize this point later when I will give you some presentation and will show some beautiful pictures, so we can a little bit speak again. But I would like to say that now such a called of gravitational lensing, write this gravitational lensing effects. Or just gravitational lensing is a very important method to investigate dark matter. So the matter which we can't see in any wavelength band, we can discover it due to this effect of deflection of the light and gravitational field. So the idea very simple. So if, for example, between observer, us, and some far object, there is such a distribution of the matter. So, and we, for example, we can't see in principle this distribution of matter, this object, because not an optical, not an X-ray in any band, but it will influence on the forming of the images of this far object which are behind of this mass. And we can even so the gravitational field of this hidden mass will influence on the light which come to us. And we can even to estimate the mass of this hidden object. And exactly this method tell us that in the universe we have a lot of dark matter which which we can't find in different bands, but we can see that there is some gravitational, something which create gravitational field and deflect the light from the far objects. So this is the point. Okay, on these things I will finish again. Beautiful picture and some summarizing we will consider in the end of my course, because I would like to continue and to succeed with one of the main idea of the course, to understand and to find the equation of universe and investigate how it works. So and if you don't have a question about this this point, we can start to build the metric of our world. No questions?
No questions.
Okay. So okay, now principle starting from this this part, we will work with cosmology. Cosmology, it's not a point to write because we start in the beginning with cosmology. So now we can write the title of this lecture. So Friedman Lemaitre sometimes just called Friedman Lemaitre, but now it's also at all names of all investigators who was working with such a kind of metric. So I will write Robertson, Walker, metric. Or sometimes just I will use F, L, R, W, metric. Or FL metric. So in principle, you can find different. What it means. Now our idea, so we have Einstein equation, we have equation of gravity in relativistic case. Our idea, what we want to solve this, to find the solution of this equation for the case of our universe. So to understand how universe.
Yeah, lunch with us.
No, unfortunately now I have my lecturers.
Okay.
Thank you. Okay. So how about the universe? And in the first, as we understand, we need to construct the metric to solve the equation. So which is what is the fundamental we will put to build the metric of our I say of our world, because okay, consider you can, when I say our world, there is equation, but they are different in principle. Maybe we will meet this equation later. So now I will put, and not only I, so it's the idea was such a way that we need to take some much more important general property of the universe. And which is important general property of the universe, we know. This is exactly, as you remember, in the beginning of our course, we spoke about the property of the universe, and we discovered, in principle, humanity discovered, that the matter in the universe on the large scale distributed homogeneously and isotropically. Okay, this is such a called Copernican cosmological principle. And sometimes just called cosmological principle. Cosmological principle. Copernican principle. Okay. By the way, this year is a jubilee of the Copernicus. I want to check. Yes. So this year is a jubilee of the because exactly 1 week ago I was on the talk about Copernicus. Yes, because he was born in 1543 and died in 1414. Ah, no, he was born 14. Yes. Okay, so the exactly the jubilee of the Copernicus, 550 years. So which this year, why this year under Copernicus. Cosmological principle, I will remind that it means that the universe is homogeneous and isotropical on the scale, so homogeneous and isotropical on the scale more than 100 megaparsec. Okay, 100 megaparsec. It means that mega this is 10 and 6 parsec. So it means that homogeneous in the tropical on the scale more than the galaxy clusters. So like this. And exactly this property we will put as the main property of the universe to construct the metric. This property is really beautiful. Why? Because now we understand that due to the gravity, the space can be curved, and curvature of the space can be really, complicated. But in geometry, we have a theorem which tells us that you can write this, the homogeneous and isotropical space is a space of the constant curvature. The homogeneous and isotropical space is a space with a constant curvature. So it means that as soon as we apply this cosmological principle, we have K, okay, not useful, not convenient for me to use R bigger, so I will write K is a Gaussian curvature. Okay, Gaussian. Which is the same R, this is scalar. Not the same, up to, don't remember, multiply and divide. Maybe this. I will write like this. I know when I can obtain formula immediately, I remember. So scalar, so it means that K is a constant. Constant. So it means that if we again to come back, for us it will be more convenient to use the value K, which is a sine of Gaussian curvature, or the same sine of scalar curvature. So we will have, due to cosmological principle, only three possibilities. So K equal +1, -1, and 0. So this is a three possibility. Okay, this is what we understand. It's already simplification, which we can now to discuss it from the philosophical point of view, but we will discuss final metric a little bit later. But now we want to obtain the metric for the and sometimes just we call the metric of homogeneous isotropical world. Metric of homogeneous isotropical world. So we want to obtain ds squared. Okay. How we can do it? So in principle, we understand that if we would like to describe, for example, the position of zero-point object, zero dimensional object, like a point, it's enough for us to put some one axis, and in principle, we can orient this point on this line. So to find the location of one-dimensional, in principle, we can describe it using a zero-dimensional object. We can describe it position using one-dimensional line, one-dimensional reference like this. So, for example, if we have some length, okay, some like this. So it's already one-dimensional object, and usually we use for this plane. Okay, so x and y. So this one-dimensional we involve to describe its position. We at least we need to involve this in two-dimensional space. So this is one-dimensional object, and we involve it in two-dimensional space. By analogy, of course, we can describe it in three-dimensional, but at least by analogy, if, for example, we have some surface, so it means some already two-dimensional object, we need to put it, involve it in three-dimensional space, x, y, z. So we involve it in three-dimensional. All time to consider some object in corresponding to its dimension, we need to put it in, or consider it in this dimension plus one, okay, to describe it. Even if you will look on analytical geometry, so to write the surface like this. And but now, okay, by analogy, we need to consider three-body world, three-body dimension, and it means that by analogy we need to put it in four-dimensional space, just by analogy, like this. So this is the main idea. Since we, as a particular case, we have a spherical distribution. So, and for us, it's much more important because spherical reference system and principle keep this property of homogeneity of the space. We can say the following. So consider the four-dimensional, or like a three-dimensional pseudosphere in four-dimensional space. In four-dimensional space. So it means that this is like a hypersphere, three-dimensional hypersphere, which evolved in four-dimensional space. In this case, just by analogy, I can write. So, okay, three-dimensional hypersphere, I need to write x1 square plus x2 square plus x3 square. And it will be, it's all, for example, if we could consider just a sphere. But since we want plus one dimension, we will put x4 square. Okay. So, and this is equation, so the left part of the equation of the sphere. On the right part, I need to put the radius of the sphere. And now I need to remind that this the radius of the sphere will change. So in principle, and we would like to find how change the radius of this kind of sphere, this world. So I put here, and as you now, I want to also remind, just a way to remember. If you will look on the first lecture, we discovered that the Hubble law brings us, and we discovered that homogeneous isotropical space, not space, in principle, construction or evolution will bring us to the things that R on T equal some scale factor multiply on some sorry, some dimension, I will put R0. So where A we call scale factor. This we obtain, see the first lectures, we obtain to satisfy the Hubble law. You remember that Hubble law, this is linear relation between velocity of the object and distance to them. Okay, and we include also Hubble parameter. Please look on this after this lecture. So in this case, I will put here R. Oh, sorry. I will put here this one. A is a function of t, okay, on R0. And I also, where R0, as we also discussed at the beginning, this is some dimension, because, you know, the dimension should be, of course, we need to put here square, dimension of the space scale. And R0, we can agree with you that it, for example, can be for now equal unity for simplification. So if we would like to consider everything in the dimension case, so we will come back it. Sometimes we just put it like a unity. It's a curvature radius of the universe in principle, it should be. And also we can put here K. This is exactly the signature of curvature, -1. So this is this equation. Mamma mia, I think we have incredible storm now. Just a second, I have to check. Okay, just observatory on the top of mountain in Naples, and when it's really some storm in the sea, it's sometimes specular. It's even complicated to go out. Okay. So so this is equation of three-dimensional hypersphere. And K, again, K, this is plus -1, 0. Three possibility. Why we can use this to write like this? Because look, when we have a K equal 1, in this case, we have a hypersphere with a positive curvature, like analogy of the sphere in two-body, in two-dimensional, for the surface. So this is analogy of spherical geometry. K -1, this is analogy of Lobachevsky space. Okay, so this is negative curvature. K equals 0, we can see what's happened. Of course, we don't like when we have in denominator 0, and we can feel ourselves uncomfortable in this case. But what it means in this case when we write the equation for hypersphere, we can see that in this case we will have a square R0 squared divided on K. And when K tend to 0, this tend to infinity. And this is exactly the limiting case when we pass to the flat space, because again it means that this radius square tends to infinity. It means that the sphere became, the radius became huge, and it means that we, in principle, come to the case of the flat space. So this is the point. Such a kind of representation allow us to generalize one by one equation for joint all these three cases of three kind of geometry. Okay, but this is not yet the metric. So now we will try to do something to obtain the metric. Okay, so to obtain the metric, we need to find the element of length. So I will write that because, as you remember, okay, I will write now del square. This is dx1 square, dx2 square, plus dx3 square plus dx4 square. Okay. So, but from the equation before, I can find from this that x4 square equal a r0 square, okay, minus 1 minus this distance square. Okay, if I will find derivative, I will do it in the next. So I will have 2x4 dx4 equal, no, everything is a constant for this. So we have minus 2x1 dx1 minus 2x2 dx2 minus 2x3 dx3. So from this we see that it will be x1 dx1 plus x2 dx2 plus x3 dx3. Divide on x4. So if we put here square, it will be square. So also I can come back now to and it's convenient. I would like for convenient to use common, which we know common spherical coordinates. So this is r, theta, and phi. So it's understandable. It will be some part which are related with the spherical coordinate theta phi and which are related with the r. So we will see now. In this case, if I will use the spherical coordinate system, I can write. So we know what is in normal spherical coordinate system we have. We can write in this case the equation of the sphere, this one. So it's in for two-dimensional sphere. We can also write in this case. I don't want to write 2 because it will in any case disappear. So I will write x dx1 plus x1, x2 dx2 plus x3 dx3 equal r. Yeah. Okay, and square it will be like this. So it means that if I will now come back to this expression, look, I can see that this x1 plus x2 plus x3 in square, it is r square. Okay, so I can write from this expression, let's call it like this. Oops. From this, I have that x4 square equal, so let's forget about r0 equal unity, so some dimension on k minus 1 and minus r square. Okay. Okay, like this. So in this case, I can now to rewrite this del square. So del square the L square equal, and for the x1 square, the x2 square, the x3 squared, so I just use the corresponding terms for the spherical coordinate system, which we know well from mathematical analysis. Okay, so if I consider like this, so I need to write dr square plus r square d theta square plus r square sinus square theta d phi square. It's again the spherical reference system. It means that this is theta, this is phi. So, and I will also have this the x4, so which I need to put, and the x4 square, it will be plus. We can write it here. Look, it will be equal, taking into account this one. So I can write this is r square dr square divide. By the way, it should be here square too. Okay. So divide on a square, taking into account this one, k minus 1 minus r square. So you can rewrite this one again. I will put it here. So, and in this case, we have for the dx4 we have plus r square the r square divide on a square divide on k minus r square. So now I will join this to summon this one and this one. Let's see. So if we will write like this, so what we will have, it will be 1 plus r square divide a square on k minus r square. So it will be dr square I square divide on k divide on right, divide on a square divide on k minus r square. So I will do following. So I will divide on r square the top and bottom. So I will have dr square a square divide on k r square, and here we have a square divide on k r square minus 1. Or I will, so okay, it's in principle, we can stop here. No, I don't like it. So let's now look, we can consider this is the same. I will put this one in denominator. So, okay, it means that I will obtain dr square. It will be, I even can write better. I can write like this. Dr square divide on, and it will be 1 minus k r square divide a square. So this I like more. And finally, we can write, if we will remind that d, the square of interval, this is c square dt square minus dl square, because we don't touch the part which are related with the time, because we touch only the part which is related with the space, because we apply this idea that is cosmological principle, which is exactly take into account of this, the properties of the space. So, and finally, if we will put here the L, we have ds square equal c square dt square minus dr square divided on 1 minus k r square divided on a square minus, and we need to put all final parts, this one, okay, r square d theta square minus r square sinus square theta d phi square. So this is the Friedman, Lemaitre, Robertson, Walker metric, or metric of homogeneous isotropical world. It's not right. Homogeneous isotropical world. Now I can allow me a little bit philosophical discussion, because we will start the next step. We have this metric, and after this we would like to see what Einstein equation will tell us about evolution of such a kind of world which are describing of this metric. So you need to remember, so when we speak about modern cosmology, which called also lambda CDM cosmology, cosmological models, or lambda CDM cosmology, about lambda CDM we already spoke, and we'll come back to this. It means that we really apply the cosmological principle. So the modern cosmology and our view on the universe, the main ground which we are using, this is this cosmological principle. Of course, and you will see that due to this fact, the solution of Einstein equation became really simple equation finally. It's a two differential equations. And of course, about philosophy of this, of course, there is question. It's right it's really the universe like this, with this property. Or this is only what we see for now. Maybe universe is not homogeneous and isotropical, but for for now, we can't exclude the possibility that this is only what we see for now using our technology. Sometimes before we were sure that Newtonian mechanics is right, and so the world is such a way. And nobody couldn't imagine that it can exist in holes or space like this. So this is in principle not only philosophical question, and sometimes there is a discussion that maybe the universe much more complicated. So you will see that it's a fortune that for now we have this cosmological principle, because really cosmology and the solution of the equation will be not so complicated. But in any case, we keep our eyes open in the sense that let's see what it will be in future, in the sense that maybe we will discover something new. Okay, maybe not. There is, as I already said before, sometimes appears the article, especially all time after launch of the new satellite, which investigate relict mission, to investigate the young ages of the universe. And sometimes some investigator says that, look, we found something which tells that universe is not isotropical. And once, sometimes ago, it was even called the axis of devil. The same was used for terroristic organization IDIL. So sometimes ago, it's also was called the devil axis, and sometimes it was used to represent devil in the sense that it really will be worse, from the point that everything will be complicated. But even complicate not only from the point that equation will become much complicated, but also from the point that it will destroy a huge part of cosmology which we understand and build for now. Because the answer on the equation why universe such a way that it's homogeneous and isotropical, we also will find it's already built as such a theory of inflation cosmology. So this is some philosophical discussion. Now we have 10 minutes, right?
Yeah.
Okay, so for this 10 minutes, I would like to prepare something to solve the Einstein equation. And just also to say a few words about properties of the universe. So, as you remember, Einstein equation, we in the left part we have I will remind. So at R(k) minus Gk multiplied on R 8 pi G C4 Tik. So this is Einstein equation which we obtained. In principle, I understand that if I already found the metric, I can find this left part. But I also need to understand this part. What's about matter? What is the matter? And now I will tell just some of the few words about this. When we consider the universe as a system, of course, the universe consists of the many objects, but we are physicists, and sometimes we are doing something from which mathematicians are very unhappy, and they say, why you are doing like this? It's not strict and like this. So, but what we can do? We try to describe reality, and reality is very complicated. So we all time try to idealize the system. But what is incredible is that finally we succeed because we can describe the reality. So for now, we also will do some trick. Trick is such a way that we can consider the matter and the universe as a sum continuous distribution. So to consider this, it allows us to consider the energy tensor, energy stress, energy momentum tensor. So T, and I will write mixed component. What we know from hydrodynamics. So in hydrodynamics, we know that we can represent it such a way that this is pressure plus energy density, UI, UK, minus delta IK multiplying pressure. So this is, so we would like to consider the matter as a continuous distribution matter in general. But there is a question, okay, which the matter which characterized by energy density and also pressure. So if we consider this like a matter. But what about velocity? So, and so when we consider this, we also can discuss this question and to agree that what means that the universe is homogeneous and isotropical. In principle, it means that the all velocity, the velocity of the velocity vector of the matter equals 0. It means that the matter is in the rest on the scale more than 100 megaparsec. Again, we write for a cosmological principle, for a cosmological scale, more the are more than 100 megaparsec. So of course you can tell, but look, but it's against the Hubble expansion. No, this is not against of the Hubble expansion because when we speak about Hubble law, about this fact that galaxies go out from us, we speak about expansion of the space. So this galaxy, no, go like this. This is related with the expansion of space. So when we speak about this velocity, velocity of the object, we speak about velocity of the object relative to the space. So this is the differences. So the extension of the space. So the extension of the space, and the motion of the object in the space. So when we speak about this, we speak exactly about the motion of the bodies in the space. From another side, we can also understand that if we could have any the motion of the matter. In this case, if we have the motion, it will finally, this motion will create and will form some inhomogeneous regions. So homogeneous regions. And in sense that, for example, if we're in the places where V is huge, in this place, the matter will, how called, removed, you know, to distribute it. English. Like make a blue, you know. And otherwise, if the velocity is small, in these places the matter will be much more dense. So due to gravity, also the working jointly, you know, the motion and the gravity. So, and in this case, if it could be motion relative to the space, relative to each other, so sooner or later we could have some inhomogeneous, the global inhomogeneous and the global anisotropical distribution. We don't see it. So, and in this case, we can tell, since I will remind that for velocity, this is what? This is 1 divided on square root 1 minus v square c square. And the space part, this is v divided on c square root 1 minus v square c square. So we can agree that we consider the case in the first v much less c, and v, which are responsible for the space part, equals 0. So from this we obtain 4-dimensional velocity, which is equal 1, 0, 0, 0. And in this case, Tik will have the following components. So it will be only kept, as we will see from this place. Okay, it will be kept only the summand, which are a component for which the I equal k. So it means that, for example, T00 equal what? P plus epsilon minus. And delta, again, I will remind that this is delta Ik equal 1 I equal k, 0 I not equal k. So, and okay, I can write minus p, it will be just epsilon. We also understand that, for example, T11 will be what? Will be it will be 0 minus p, okay, minus p. The same for T22 and T33, so equal. So, and I can write the component of the stress energy tensor. So it will be epsilon minus p minus p minus p, and here all 0. I will draw like this. It's understandable that we need just to put zeros in this matrix. This is a component. This is energy. Okay, you can write energy stress tensor for the world, which is again which is correspond to the homogeneous and the tropical distribution. So for such a kind of universe, such a kind of model of universe. So you can see, and maybe you can feel that it's such a trick. So we simplify all time. So, but it looks like God made the universe such a way that you know, it's became not so complicated. But we will see why later. Okay, in principle, we prepare it now for this solution of Einstein equation. On next lecture, we will solve, I hope, and we will, yes, we will solve the Einstein equation for this case. For the general case, I mean, later we will discuss which exactly matter we need to consider. And I think in the next lecture, I also will give you some home tasks. So it's important to be present on the lecture because we will find the one component of Einstein equation, another it will be for home. I will just use because it's a long procedure. Now I will make a screenshot of presence. If you have some question, please ask. No any questions? Are you here?
Yes, we are here, but no any questions.
Okay, let's hope that it's understandable. So, but be more active. So, if you have some question, don't be scared to ask. Again, in any language. Any language is acceptable. So, not obviously in English, in Ukrainian, if you want. So, okay, no question. Okay, let's hope that next time some question will be, or maybe it's understandable. So also I would like to say that I received the answer on some previous home tasks. I will collect all of this during some time because it's a complicated business to take into account everything. Conclude also. Now we have, I discovered that we will have exam through the Moodle system, so everything under control. So we will see. Okay, so we will meet each other on Friday. Yes.
Yeah.
Okay. Good day. Good.
Thanks for lecture and goodbye. See you Friday.
Goodbye. Okay. Goodbye.